Hello everyone, welcome to another video in the Raspberry Pi 4 bare metal assembly programming tutorial series. So in our last video we were able to blink a light on and off and on and off and on and off as long as we had power going to the board. However, we hard coded that to be on GPIO21. So today what we're going to do is make it more generic so that we can specify any pin we want, and then it will do all the heavy lifting, all the work for us. So just to recap our code, we've talked about this stuff over and over and over. Let's get into new stuff. You can see that we're setting up our base address, which is this. We talked about how we needed to have one located in this little bank here for GPIO21. To do that, we started by having it here and we shifted it over 3 times to the left, and then we stored it in the function select2. And then after that, once our pin was an output pin, and we're going to go into this in more depth, so if I'm going too quick, don't worry, we will go into more detail here because we're going to be generalizing all this code. Anyway though, we set up this number, and this meant turn on this specific pin now that it's an output, and then the clear meant turn it back off, and then we have a delay here. We're not going to touch the delay in this video. We will touch the delay in a future video though, because we want that to be accurate instead of just a really large number. Anyway though, let's work on generalizing all of this code here. First, let's move some of these things that are very GPIO related into their own file. So let's create a GPIO include file, and we will copy over all of this, pasting it into there, and then let's we will want to include that file. Now this code will not be absolutely perfect. We're not going to talk about include guards in this code because we don't necessarily need it. However, in the future we will definitely be adding include guards and things like that to make sure that our code isn't duplicated and wreaking havoc. I'm going to cut this out and paste it into here, but we are going to become a little bit more detailed because since we're going to be more general, we want to make sure we have more documentation. So the first thing is, in the previous video we talked about why we're using FE200,000. I have a comment in here to include why we're doing that. So the FE part is coming from, I guess I can put in here that this is doc1, and then this is doc2, and then therefore this would be doc3. So doc3 page 6, and then the offset of the 200,000 bit, that comes from page 66. Alright, so we got that documented. Now the next thing we want to do is we should expand this picture out a little bit because we were specifically working with GP function select 2 last time. However, there's more than just 2. There's 0 through 5. So we will clear this out, and we'll duplicate this. So first one here, we will replace the number 2 with the number 1, and that's going to mess up 12. Easy enough to fix. Duplicate that again. We will just delete all these little ones. All right. This was probably the worst one to copy. Sorry about this, but it gives everyone a chance, I guess, to look at what we're actually doing. So replace 1 with 3. Replace 1 with I know that selection thing is sometimes a little tricky. 4. And then this one will replace 2 with 5. All right. So we know that, and then we also know that this is GPSEL0. This is GPFSEL1. And I'm going to just copy and paste. Two, 3, 4, and all the way up to 5. And then the offsets that we'll be using is for 0, it was an offset of 0. This was an offset of 4. This was C, 1, 0. Five would have been 1, 4. All of this comes from our peripheral manual that we looked at before, page 66. So we got 0, 4, 8, C, 1, 0, and 1, 4. All right, so let's start just generalizing this little bit of code. What we'll be using is macros to do that. So we'll put in macro, and what's the name I came up for this? I called it GPIO pin mode setter. And it will take in the GPIO number and then the mode. So previously we were only using mode 1. However, when we look at the documentation, there is more than just mode 1. There is, which is output. There's this mode for the alternate function 0, and it goes all the way to alternate function 5. So what we will do is we're going to include this as well, because our memories might not always be perfect, and when that day comes, we will still know what we're doing. So we'll call this GPIO mode, maybe pin mode. Yeah, I like that better. GPIO pin mode. Input was 0. Output was 1. And then there was alt func 1, or alt func 0 rather. And that was the number 4, represented by, if you're wondering where I'm getting this from, I do try to expedite things by taking notes ahead of time so that you don't have to completely watch me struggle. All right, so this was 5, 6, 7, 3, and 2, and the binary way of showing that was 101, 110, 1111, and like that. Okay, so we have all of our modes now. This will be used for the mode, and then let's start writing our logic. So the way we would want to call this is, we'll start out with 21. That's currently what we're using, and then instead of putting in a 1, we could do that. Let's put in our newly found output. Perfect. All right, let's take this code and put it in here. Now the way these work is they're not like a regular function where you branch over to here and then you return. This is more like an inline function, a copy and paste. So this specific line will be replaced by all of this with the values that we're looking for. And that's all done during the compile stage as well. And we have the ability to do math at the compile stage. So we're going to start taking advantage of a few of these different things. So the first thing we need to figure out is how big is our mode. And we know that it is a mode size of 3. It's 3 bits. Now we could just say that for like modes per register that it is 10, because there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we could do that. However, some of this code we're going to want to be able to reuse in a future video. So what we're going to do is we're going to actually do 32 divided by 3. Now we're using integer division. So I suppose we probably should talk about division real quick, the way that this will be working for us here. So 32 comes from the fact that there's 32 bits in a register. So if we do 32 divided by 3, that's the same as 32 divided by 3, which is the same as when you go inside of this little underscores maybe? No, we'll use dashes. The long division that we probably haven't done in a fair amount of time. All right, so 3 goes into 3 once, and that gives us 3 minus 3 gives us a 0, but then we drop down to 2, and when we do the 3 goes into 2 0 times. Sorry, had to think about it. I haven't done this in a long time either. 3 goes into 2 0 times, but then we have a remainder of 2. There we go. Obviously, I have not done long division in a while. It took my brain for a split second to remember how to get 10 out of this math. So sorry about that. But anyway, this gives us 10 remainder 2. Now normally you're probably used to dropping down a 0 and having a decimal point, but I did this for a very specific reason. We will come back to remainders in a little bit. Needless to say though, 32 divided by 3 will give us the number 10 because this is integer division. So I said we could use the number 10 because we counted it out, but we can do this and this will give us the same number 10. All right. Now we want to figure out what is the registry number or the register number that we want. So what I'm talking about is if we have pin 6, we want 0. If we have pin 16, we want 1. If we have pin 21, we want a 2. Now the way we can do that is, I'll call it a registry number. We take our GPIO number, so our 16s and our 21s and whatever number they pass in, and we will want to divide it by this modes per register, which we know is going to be the number 10. So if we take 21 divided by 10, doing similar math to this like we had before, we know that we will get 2 remainder 1. So indeed, previously we used the number 2 here, and that will give us the number 2 with our test case that we're working with. So that's great. Now, more specifically, we want to know the register's offset address. Or I can just call it offset. Register offset. Well, the way we do that is we are going to take this registry number of 2, and we know that we have an 8 here. So 2 times 4 gives us 8, 1 times 4 gives us 4, 0 times 4 gives us 0. And yes, this math checks out. So we can do registry number times 4, and this will give us our registry offset. You'll remember previously we hard-coded in GPF-SEL2, but now we have calculated it, so we will use that instead. All right, great. So that is all good to go. Next, let's figure out the shift position. So by doing this, I told you that it gave us 2 remainder 1. And I said we were going to talk about remainders in the future, so let's actually switch it to our use case. So we're going to have 10 it's going to be 21, yes, 21 divided by 10 would give us, it jumps on top, then it jumps inside the box. Okay. I'm sure there's people out there that are like, this is really easy, why are you struggling? It's been a little while. I know what I want to say, I just want to make sure I say it right so that people don't leave this confused. The reason for that now is 10 times 2 gives us 20. And 21 minus 20 gives us a 1. So remainder 1. We're going to care about both of these. Previously, we cared about the 2 because we wanted to find out our registry number, and that gave us that bit. Now, we want to figure out which little bank of numbers in this, essentially it's an array, do we care about. And we know that it's not the 0th entry, it's actually the 1 entry. Well, fortunately, this remainder 1 comes into play. And if you were to work with 27, 27 divided by 10 remainder would give us a remainder of 7. So this helps us figure out how far we want to go over. Now, whatever number we determine, in this case 1, we want to multiply it by 3 because that is our mode size. So first of all, let's do that little remainder bit. Shift position, I'll call it, is going to be GPIO number mod, which gives us our remainder. And if you're wondering what are all of the capabilities that we can do in FASM, in the documentation under expression values, when you go to the website, you can see that it can do mods in here somewhere. There it is. So addition, subtraction, multiplication, integer division, mod, shifting to the left, shifting to the right, not, all sorts of stuff. We have lots of capabilities. And the cool thing is this all happens during compile time, which means it will not affect runtime. Okay, so this gave us the 2. This gives us the 1, but we actually need a shift amount. And what we'll use is shift position times 3. That 3 comes from the fact of how large these are. So if it's 0, 3 times 0 is 0, so it will drop it in exactly where it was. If it's 1, like it is in our case, 3 times 1 gives us 3, and lo and behold, that's where this 3 will be dropped in, because it starts here, 1, 2, 3, it's now in the correct little bank of numbers. So instead of 3, we're going to put in shift amount, because this will always be the number that we need. Now you might be thinking, all right, perfect, we're good to go. And kind of. If we're always only setting up 1 pin per bank, we would be good to go. But let's say you want to set up GPIO 20 and 21. Whichever one runs last will win. That's the one. So the reason for that is let's pretend we're working with 20. So this gives us the number 10 like we had before. So we take 20 divided by 10, that gives us 2. 2 times 4 gives us our 8th address, which we're using. Perfect. All right, our shift amount now is going to be 20 mod 10, which is a remainder of 0, so that's 0. 0 times 3 gives us 0, so we take our mode, not the number 1, our mode, and we shift it by 0, so 20 will be perfect. We save it, we're ready to go. Now we want to set up 21. We go through all that exact same process, except now we pass a 1 if it's an output here, but notice that the 20 is all zeros. It's not pulling the current settings back. So we have to change our code to pull back the current settings, that the pins of what they're set up as, and then we want to modify that number and then store that number back. So what we need to do is we need to load that number into W1 first. So what we've done is we'll pretend that this is the mode that we have previously set. That's alt function 1, I guess. So pin 20 is 101. Now we want to make 21 a 1. How can we do that? Well, first we're going to pull this information out of memory, and if you want to look in the manual, that will be located under the data transfer instructions. You can look for LDR, and you can see how those values are pulled out of memory and stored into a register. It's very similar to store, STR. It's the exact opposite. Instead of storing a value, like we talked about previously, we're going to pull the value out. All right, so we have this number currently in W1. Now, we could just shift in whatever this mode is and save it. So that would work, right? Because if it's a 1 current, or if we want to save a 1 in there because we want to save an output, we could just shift in a 1 and we'd be good to go. But what if we previously set this pin to be alt function 0? So this was set to alt function 1, this was set to alt function 0. If we move in a 1, we will turn it into that, and that is not the right thing for us. We want it to be this. So what we have to do is we have to find a way to clear this value out ahead of time so that it's blank, and then we can fill in whatever we want. And if you're thinking, oh, bit masking, you have thought correctly. We're going to do bit masking again. So let's copy this value out of here so we can do a little bit of illustration. Now, we talked about bit masking in a previous video, and I guess just the really high-speed version is if you're painting something, let's imagine a wall with a window in it, and you don't want the window frame to be painted along with the wall, what you can do is put masking tape over the frame, and then you can paint to your heart's content, and when you peel the masking tape off, whatever underneath there will remain. And that is what we are going to do here. So we know that if we have this number that when we AND them together, 0 and 1 will give us a 0, and that will happen a lot. 0 and 0 will give us a 0, and then 1 and 1, 0 and 1, 1 and 1. So this will maintain this previous number, but it will blank out where the zeros were. So even if this was previously this number, 1 and 0, when you AND them together, it will give us zeros. So I guess for those that are super visual, the number we will end up with when we're done ANDing these two together is this. No matter what this number is, this field will always be cleared out. All right, so you might be thinking, how do we create this number? Well, very cleverly. So first thing we need to do is we know that we need 3 zeros in a row. And for sake of ease, what we're going to actually do is create the exact opposite number. We're going to create this number, and then we're going to knot it. So when you knot a number, whatever was a 1 becomes a 0, whatever was a 0 becomes a 1. So when we say that we want not this number, it will give us the number we're actually looking for. So now we have to create this number. And we know that we have 3 1s in a row. So first let's create just this little bit, and we'll imagine that it's actually over here. So how do we create this number? Well, one way that we can create this number is, let's call this mask. We can take our mode size of 3 and we can shift a 1 over 3 times. And it is this inside of FASM. Instead of LSL, it's for shift left. Actually kind of like that naming better, but anyway, this will create, for our example, it will create this number. Because the 1 was here, we shifted it 1, 2, 3 times, and it gives us this number. You might be thinking that is completely the wrong number. But what if we subtract the number 1 from it? If we subtract 1 from it, we end up with this number. And that is the number that we're looking for. So that's what we're going to do. After it's done shifting whatever our mode size is to the left, we will subtract 1, and that will give us the actual little mask that we're looking for. All right, so we have determined how to get our mask, and you might have guessed it, the way that we're going to actually get into the right spot is we're going to shift it over the same as the shift amount. So let's start writing this code. We've loaded this number, whatever it is, into W1. Now into W2, we are going to move our mask. All right, so now W2 will contain this number right here, this whole thing. We'll have 3 ones located in the 0 entry or 0 index spot of our array, I guess you could call it. Next, we're going to use a new instruction we haven't looked at yet. So let's go to the manual under General Instructions, and it's MVN, which is bitwise not. The way it works is it allows us to, this is our destination, so we can start with a register, and then we can shift it as well. And the shifting is the range of the full bit range, 0 to 31 or 0 to 63, depending on if it's 32 or 64 bit. So we can kind of do 2 birds with 1 stone here. We are going to move not. The W2 is our destination. W2 is what we're starting with, so we're starting with this number. And we can include a shift, so we will shift it over. Now remember this shift, if it's 1 times 3, it would be 3, so this little triplet here will move over 1, 2, 3. And that brings it into the correct spot, but it also will not it. So by doing that, it will convert it into this number, the number we've been looking for. Perfect. And we have to run the AND instruction, just like we do whenever we are dealing with this specific type of bit masking. So we'll do AND W1, W1, and W2. So what this is saying is take this number, which is in W1, and take this number, which is in W2, and sort into W1. It's kind of like, it would look like this, W1 and W2. So this is essentially what we are doing. All right. Once that is done, all the rest of this can remain exactly as it is. So let's step through it once and just make sure that our logic makes sense. We take 32 divided by 3, that gives us 10. And that's because this is 3. 32 divided by that, it's integer, so that gives us 10. And we've counted, there is indeed 10 in each one of these. We'll use the number 21 as an example. 21 divided by 10 gives us 2, because there's no decimal places that are kept. We take 2 times 4, that gives us 8, and that is the number we're expecting to see. So we are able to use that number. So we take whatever number was there previously, something like this, we store it into W1. After that, we generate this mask, and the way we do that is we create the opposite of this number. So we start out with 3 ones, we shift it into the right spot, we knot it, we ended up with this number. That covers all of this part. We AND the 2 of them together, and that will give us this number with this one spot that we want to work with cleared out, so it's all zeros. And then we fill it with what we had before, but we'll walk through it. If it's an output, for instance, it's a 1, we shift it over 3 times, and then we store it back where we got it from. So we've preserved whatever pin values were there previously, and we've added in our new pin value. All right, so that's probably the hardest part of this whole video. Everything else from here on out should be a little bit easier, and it will be using actually a lot of the same type of logic. So let's see, I'll look at my notes here. Yes. So what we need to do now is we'll work with the setter. So I have this called macro GPIO, set output on. We want to turn it on. We just need to know the GPIO number. And in this case, when we look at the documentation, the setter is based on this little bit here. So GPIO 0 through 31 is all in the first one, and then the second one does 32 through 57. We do not have to worry about what the previous settings were, because if we pass in a 0, it has no effect. So if we were to, we need a little picture, don't we? And we don't have one. Did we have one here that we, if we did, we deleted it. So we'll create a new one. I'm guessing this was 20 and this would be 2C. I'll confirm that before we, oh, I have it in my notes. 20, yep, and 2C. Okay, perfect. All right, back to illustrating. So if we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2. So if we wanted to turn on GPIO 0, and it's an output pin, we would just set this as a 1. Now later on, if we pass in this number, which would be GPIO 0, 1, 2, 3, 4, we want to turn on 4, 0, GPIO 0 will not turn off because the 0 has no effect according to the documentation. So we don't have to worry about all this, where is it? Here it is. We don't have to worry about all this preservation stuff because the computer takes care of it for us, which is a very wonderful luxury that you probably never thought would be a luxury, but it is. It's a luxury. So we'll take advantage of that. So to set, what we need to do is we still need to figure out the registry or the register number, whether it's a 0 or a 1. And the way we do that is this time we take our GPIO number and we do not need to divide it by 10 because we're not working with little triplets, we're working with each individual bit. So we could start with, we can divide by 32. So we'll just check that once. Let's say it is 31. 31 divided by 32 will give us the number 0. And if it's 33, 33 divided by 32 will give us the number 1. Okay, yep, that math checks out. Now we need to know the register offset, and it is going to be our register number times 4, just like we had before. However, there's a caveat. So this part is what we're expecting, but it's not based off of 0, because let's imagine that this gives us the number 1. If we take 1 times 4 and we use that as our offset, we know that that gives us this number, and that's not what we're working with at all. But if it gives us 4 and we add it to this number, we end up at this number. So we need to use this as an offset. And that's the way that we do that. So if it's 0, it will be this number, 1C. And if it happens to be a 1, 1 times 4 gives us 4, plus 1C will get us to 20. Perfect. So we now know the address we want to work with. So eventually what we'll be doing is we will be storing W1 into our X0 with our register offset, just like before, but we need to create that number like I showed before where we shift it over. And the way we're going to do that is we are going to move into W0 the number 1, and then we will shift it over that shift amount that we want to we still need to calculate that, but that is our goal. So let's calculate that now. Shift amount is going to be our GPIO number mod 32. So if we take 31 divide by 32, we get 0. And if we do the remainder, we know that we get a remainder of 31, which is perfect. That's what we need. So we will plug that value into there. Now, I'm going to also add in this. And the reason I'm going to do that is this the most efficient code in the absolute world? By doing this, no, it's not. But if we turn something on, and let's say this delay, right now it uses x2, but let's say in the future it uses x0 for some reason, which it very well might in the next video when we have an accurate delay instead of just a large number. All of a sudden, if x0 is some other number other than what we think it's supposed to be, it will be taking whatever that random number is and it will add our calculation to it, and then it will save it at that address. And that has happened to me when I was preparing this video, and yeah, it's not an enjoyable thing trying to figure out why the program just randomly dies at a memory address and nothing is working. So is it super efficient? No. And I guess when you're doing handwriting assembly too, there is a balance. There's a balance between efficiency and readability and debugging. When you have a compiler like a C compiler, it thinks of these types of things for you and it takes care of it automatically, and that's why they say that generally a compiler is going to write more efficient code than you're going to. But if you look at the code a compiler spits out, it's not super easy to read, and that's because it's not designed to be read by a person. But if you're writing the code by hand in assembly and you need to be able to debug it, and later on you need to be able to read it, then legibility kind of counts. So you have to figure out where is efficiency extraordinarily important and where is it not super important. So if we add like 2 clock cycles, or even if it's 4 clock cycles, in the grand scheme of things, I mean, this chip's running at, what is it? It's going to be like 500 megahertz or something. Maybe it's not running at that right now. We haven't tweaked with the clock yet. We haven't tweaked things. So it might be at like 52 megahertz or something. Needless to say, we're talking about billions of cycles per second. If we add an extra 4 here or there, it's not really going to be it's not going to really mess a whole lot up. Now, if this was a critical application that you, down to the nanosecond or whatever, needed to make sure that this output is turning on and turning off, then you have to be more careful. So again, it's the application you're working with. This is kind of a crude application. If the light is a couple microseconds longer than what we think it is, it's still blinking at whatever rate that it's close enough for what we're working with. So again, code according to your application, and over optimizing will be a nightmare if you optimize things that don't really matter that much. All right, so there's my little spiel. Let's finish this up now. We also want to do set output off. So let's do that too. And this code is going to be basically identical, except instead of working off of set as a base, we will work off of clear as a base. So we can put in here 21, and for the off version, we can also put in 21. Now, if you were writing this code by yourself and it hadn't been already tested out, we would have been assembling a lot more along the way. When we started out, we would have just have proven that this part of the code works and assembled it and tested it. And then if that worked, then we would add in this part and make sure it still works. And then with this part, we would turn it on and find out if it works. And we need to be very deliberate in our steps, because the assembler just says we did something wrong. Well, what did we do wrong? MVN W2, W2 shift amount. I know what we did wrong. LSL. Okay. Back to what I was saying though, it just says that it assembled. It's not like C where it says, oh, your logic doesn't make sense. I guess C doesn't always do that either. C# would, or Java, or probably Python. I don't work much with Python, so I'm not sure on that one, but I'm assuming any super high level language, the compiler or interpreter or whatever it is going to kind of hold your hand and say, the thing you're doing is probably not going to work. As you get to these lower levels, it just tells you whether or not it can encode it. It doesn't really do any checks for you. So you want to be pretty deliberate with your checks, and every step along the way, make sure that what you're doing actually is working. The nice thing is, now that this is created though, we can use it in the future. So it starts out really hard because we're writing a lot of boilerplate code, but once these things are written, then we can start using them as tools to make more and more complex things, and it should become a little bit easier in theory as we go along. Anyway, we have assembled this. Let's test this now and make sure that what we have written actually works. Okay, so we're going to test this with GPIO21 to make sure everything is continuing to work. So we'll plug it in and it's booting up. And let's see. Yep, everything is continuing to work. So we're ready to move on to test another pin. Okay, so that worked out for us. Perfect. Let's work with a different pin now. So if we look at this, we did GPIO21. Let's test out GPIO3 next. And one thing to notice though is 21 was on the right hand side and the ground was on the left. This one, the pin's on the left hand side and the ground's on the right. So since this is an LED, it'll only allow the current to travel in one direction. So if you forget to swap those pins, the LED won't turn on, and it's not your code, it's your setup. So let's test that one next. Okay, so let's test this out. You can see that we're way at the bottom here. We need to flip that over. Also, that ground is on the wrong side, so I'll do this in camera view here of flipping the ground to the right hand side to match that new layout. And we go down 3 pins so that we are using GPIO3. Now we'll plug it in and we'll notice something a little different. The light comes on right away. That's because the default for GPIO3 is different than GPIO21. However, now it is blinking on and off, which means we have successfully achieved our goal. Our code is generalized. All right, and since that was working, next let's try out pin 42. And you might be wondering, what is pin 42? So if we ask Google, you can see that Google says 42 is the answer to life, the universe, and everything. Um, no, that's actually not what we're working with in this case. What we're working with is that little LED, the activity LED, the green one. When you plug in the board itself, where's that little image? Oh, they don't show them on here. So there's a red one and a green one. The red one means there's power, the green one means there's activity. You may have noticed when you were testing that it will flicker on and off quite a bit until our kernel is loaded, and then it'll just turn off and never turn on again. The reason for that is the kernel is not telling it to turn on. The bootloader does. The bootloader is showing activity and that it's doing things, but our kernel that we've written is not. 42, GPIO42 is not listed on here anywhere, but that is the one that goes to that little LED on the board itself. And I think it's kind of neat that we can have full control over our Raspberry Pi, that we can even turn on and off LEDs on the board itself. So let's see here. We put 42 in all the proper places. We'll save that, and let's test that one out next. Okay, so we have a Raspberry Pi 4 here, and what we're going to do is we will plug it in, and there's the lights right there. Let's cover up the red one so it's easier to see the green one. Now it's still booting up, but there. Yep, it's blinking on and off, and it looks like it's a pretty continuous. It's not flickering anymore. So we did it. We have controlled the LED on the board itself. Okay, so we covered a lot of ground in this video today. We were able to generalize our code so that we can set our pin modes. We were able to turn our output pins on and off. We explained how all this code works. We put it all in a separate include file that we included up above. And we even were able to turn on as a bonus a GPIO that's not actually documented. That's why I didn't take you to the peripherals page. It does not explain how to turn on that activity light. So we were able to even go a little bit above and beyond the documentation, which is always a little bit of fun. Anyway, I hope you enjoyed this video. I hope that you're encouraged to see that you can do more and more and more with your Raspberry Pi, and we're going to continue to expand upon this. So I look forward to seeing you in future videos.